Now let's see how we can determine the fugacity. We have the basic equation dg is equal to vdp minus sdt. At constant temperature, this equation becomes dg is equal to vdp, which is applicable for ideal gases. For ideal gases, we'll substitute v is equal to RT by P, and this equation becomes dg is equal to RT by P dP, or that is equal to RT dln P. In order to use this equation for real gases, we have to substitute P by the fugacity F. That is dg is equal to RT dln F. Okay. So dg is equal to RT dln F and dg is equal to vdp. They represent the same quantity, same function. Okay. So now we can equate this to why we are equating is that at very low pressures, real gases behave ideally, and with this assumption we can equate dg. Here let it be 1 and let this be 2. At very low pressures, we can assume that real gases behave ideally, and equations 1 and 2 represent the same function, and hence RT dln F is equal to V dP. RT dln F can be equated to dP. From this, we can write dln F by dP is equal to V by RT. Let this equation be here. Now, let's introduce a new function alpha, which is defined as RT by P minus V. Okay. So, for real gases, RT by P is V and V minus V is 0 and alpha is 0. For ideal gases, for real gases, alpha is RT by P minus V. From this, what is V? Is RT by P minus alpha. Okay. Substitute the value of V in equation 3. RT dln F is equal to RT by P minus alpha into dP. Okay, now we have obtained a relation RT dln F is equal to RT by P minus alpha into dP. Now, if we are integrating this equation between a very low pressure of 0 and a given pressure P, which is also very low at constant temperature, we can write integral RT dln F is equal to integral 0 to P RT by P minus alpha into dP. Okay, R and T being constants, RT integral dln F is equal to RT is a constant, integral dP by P between limit 0 to P minus integral 0 to P alpha d. Okay, removing the brackets. We have just removed the brackets here. Okay. So what is integral dln F? Ln F. So we have here RT ln F is equal to RT integral 0 to P dP by P minus integral 0 to P alpha d. Dividing throughout by RT. Here RT and RT cancel out. We have ln F is equal to RT and RT cancel out. Integral 0 to P dP by P minus 1 by RT integral 0 to P alpha d. So now we have an equation for ln F. If we can find the right hand side of this equation, just by taking the antilog, we can calculate f. So how do we calculate the right hand side of this equation? Integral 0 to p dp by p is ln p, that we know. So we'll write it. Ln f is equal to ln p minus 1 by rt integral 0 to p alpha d. So how to determine this integral? Integral 0 to p alpha dp. To do that, we can determine alpha at various temperatures. What is alpha? RT by P minus V. For real gases, calculate alpha at various temperatures, at various pressures, and plot a graph between alpha and P. Okay, so when we plot a graph between alpha and P, we'll get a graph like this, and this shaded area will give you the value of integral 0 to p alpha dp. Okay, the area of the curve will give you the value of integral 0 to p alpha dp. Okay, that's how you determine ln f. Ln f is equal to ln p minus 1 by rt integral 0 to p alpha dp. From this equation, we can calculate f by just by taking the antilog. Okay. So ln f is equal to ln p minus 1 by rt integral 0 to p alpha dp. Okay. So now we saw how we can calculate ln f from a plot of alpha against p. But at very low pressures, the value of alpha is found to be a constant. Okay, at very low pressures, alpha is found to be a constant. So we cannot use this. In this integral term, alpha is a constant, and hence this becomes ln p minus alpha by rt integral 0 to p dp. What is integral 0 to p dp? That is p. Therefore, this equation is ln f is equal to ln p minus alpha p by rt. Taking this ln p to the other side, we can write ln f by p is equal to minus alpha p by rt. Ln f minus ln p is ln f by p. Ln f by p is equal to minus alpha p by rt. Okay, so we this is at very low pressures. This is the case at very low pressures. Okay, when we defined fugacity, we had introduced that limit p tends to 0. Limit p tends to 0. F by p is approximately equal to 1. Okay. Mathematically, if we have a function like that, limit x tends to 1, ln x, that is equal to x minus 1. Similarly, we can write ln f by p limiting f by p tends to 1 is equal to f by p minus 1. Using that mathematical equation, when f by p tends to unity, ln f by p is equal to f by p minus 1. Using that equation, we can write f by p minus 1 is equal to minus alpha p by rt. Okay, so what have we done here? We have just introduced a mathematical approximation, that is, when if there is a function like this, limit x tends to 1 ln x, then that is equal to x minus 1. So using this, limit f by p tends to 1, ln f by p becomes equal to f by p minus 1, or we can write f by p minus 1 is minus alpha p by rt. Okay. Or from this, f by p is equal to 1 minus alpha p by rt. Okay, but we have alpha is equal to rt by p minus v, or f by p is equal to 1 minus rt by p minus v into p by rt. Okay, so this now becomes f by p is equal to 1 minus rt by p into p by rt is what? 1 minus pv by rt. Okay, this is 1 minus 1, 0, plus pv by rt. F by p is pv by rt, or f is equal to p squared v by rt. Thus, we can calculate the value of fugacity without much difficulty at moderately low pressures. This equation is applicable only at moderately low pressures. At higher pressures, we have to integrate this equation, integral 0 to p alpha dp, and for doing that we have to plot the graph between alpha and p and take the area of the curve. Okay, this is how you determine fugacity, first by graphical method and the other by an approximation. F is equal to p squared v by rt. This equation you can use in for solving numerical problems in fugacity. Okay, so by the equation that we have derived, ln f is equal to ln p minus 1 by rt integral 0 to p alpha dp. Okay, so bringing ln p to the other side, ln f minus ln p is minus 1 by rt integral 0 to p alpha dp. From this, ln f by p is equal to minus 1 by rt integral 0 to p alpha dp, and in order to solve this equation, we are drawing we are plotting a graph between alpha and p, and we are taking the area of the curve. We can evaluate this integral 0 to p alpha dp in another way by using the compressibility factor. You know what compressibility factor is? Compressibility factor is pv by rt. Okay, from this, what is V is equal to, V will be equal to RT into Z by P. RT into Z by P is V. But alpha is RT by P minus V. Let's substitute this term for V. Alpha becomes equal to RT by P minus RT Z by P, or this RT is common and 1 minus Z by P. Okay, let's substitute. ln f by P is equal to minus 1 by RT into integral 0 to P RT into 1 minus Z by P into D. RT and RT cancel out, and what is left is ln f by P is equal to integral 0 to P, minus when taken inside becomes Z minus 1 by P into dP. Z being a constant, compressibility factor being a constant, this equation becomes equal to Z minus 1 into ln P. ln f by P is equal to Z minus 1 ln P. And using this equation also, we can calculate the value of f provided